Andy McIntosh with us tonight. And Andy tonight is going to be looking at the subject of science, mathematics, and beauty. And so this is a really interesting talk, and hopefully it'll really stir your minds. And so, Andy, thanks for being with us tonight, and I'll hand back over to you.
It's my pleasure to be with you, Simon, and I'm very grateful for all that Answers in Genesis are doing during this extended period of lockdown, particularly for Leicester, where we're still not quite come out. But we don't know what the future holds on those things, but we're prepared to make good use of the opportunities that we have to speak about creation and to speak about the importance of understanding truth based on a creation and biblical perspective. This talk, Science, Mathematics and Beauty, is something which is not necessarily needed for, you think, for people who don't know anything about equations, like I've put there. Well, don't you worry too much about that, because there was somebody who said this: I'm neither especially clever nor especially gifted. I'm only very, very curious. Now, maybe that's you. You know who said that? You probably, some of you know. It was none other than Albert Einstein. Well, but he started by being curious. And to be frank, he built up his knowledge just by asking relevant questions, trying to understand what was going on. And eventually, of course, he made some incredible discoveries. One of these things that he said was that most incomprehensible thing about the universe is that it is comprehensible. In other words, the universe is made to be discovered. If we were in the other parts of the galaxy, we wouldn't be able to have a dark night. It would be so bright with stars. And yet, if we went too far out, it would be dark completely and you wouldn't see hardly any. So God's placed us in the galaxy. The solar system is placed at the right point in the galaxy such that we can comprehend our galaxy, and of course beyond that, the whole universe. We don't understand everything, but we love to be curious, and that's what he was doing. I'm going to go through a number of things which I put there. We may not get through it all in the same level, but I just want to sort of guide you through the amazing concept of mathematics. There's no test at the end, so don't worry. And if there was, it's not my test. So if Simon asks you lots of questions at the end, that's not me doing it. I just want to enthuse you with the connection between truth and mathematics. Mathematics is a very precise language. But before we consider that, I want to consider abstract thought. What is it? What is it to think about things which are not really concrete? You can't sort of hold them in your hand, and yet they're real. Even C.S. Lewis, who was no mathematician, said this. He said, nature is quite powerless to produce rational thought. Not that she never modifies our thinking, but that the moment she does so, it ceases for that very reason to be rational. In other words, rational thought is not just the production of chemistry, even though your brain's whirring away with neurons and all the rest of it. That isn't really the definition of thought. Thought transcends the vehicle, which is the brain that you're using in order to think. That's the point that he's making. And if you could say, oh, well, he's making that noise in the corner because, you know, he's just eaten a boiled egg and it's not agreed with him very well, you know, and he starts rumbling around, then you'd say, well, that's due to the boiled egg and the bad eating that he's had. Or sadly, some people, of course, really do suffer from Alzheimer's, and they find that they've lost their mind, basically. And they will make a noise and they put words, but then there is no real rational thought there anymore. And you can attribute that to some sort of chemistry, some medical reason. And as he says, the moment it ceases, the moment you can trace it to something like that, then you cannot say that it is rational thought. Rational thought is something which, although it's using the brain, is not defined by the brain. For as soon as we're seen, as soon as a train of thought loses, let me read that again. For us, as we have seen, a train of thought loses all rational credentials as soon as it can be shown to be wholly the result of non-rational causes. So there's a person who wasn't a mathematician understanding that abstract thought is not defined by the vehicle in which it sits. I'm using a computer, right? The computer itself is not that which is making all the talk, which is being displayed via Zoom and via Facebook. That's because my mind has put this together and I'm conveying it, and that's the same issue. So we need to realize that rational thought is not the same as the neurons. Even Haldane, who never became a Christian, was very eminent in his time between the wars in chemistry. He was no Christian, but he said this: if my mental processes are determined solely by the motions of atoms in my brain, I have no reason to suppose that my beliefs are true. And hence I have no reason for supposing my brain to be composed of atoms. And so, you know, if as we shall hear later, Dawkins says, my brain is just a lump of meat, then why should I believe anything he says, right? If an atheist comes along and says to me, you know, my mental processes, like Haldane is saying here, are just not due to rational thought, but just then how do I know that my beliefs are true? Is it just due to the apple that I ate a few hours ago? What is it that really makes me to have rational thinking? He could see the dilemma that he was in his non-Christian viewpoint that Haldane had between the wars. So what defines information is an important issue. Is it the DNA molecule, the DNA code, the energy stored in the molecule, the DNA polymerase? Don't worry about all these terms, but you know that there is a DNA double helix, which is right at the bottom of really the storage mechanism, which actually works the biochemistry, which makes everything in our bodies. Well, where is it that the information is there? Because Crick and Watson, when they discovered this over 50 years ago, getting on towards 60 years ago now, when they discovered that DNA double helix in the Cavendish laboratory in Cambridge, they realized that it was rather like a storage device, which we would say now, not then, but we would see it as something like a storage device in a computer. They could see that it was a coding device, and the information that it was carrying was not defined by the biochemistry. And it's none of the above, you see, it's non-material. It's the same sort of issue. It's not now talking about abstract thought, we're talking about abstract coding. Now, abstract thought then is not defined by physics and chemistry, neither is it defined by the brain and the firing synapses, neither is it defined by the DNA chemicals or even by the coding itself. The coding is actually of a message which is going on in our chemistry, in the biochemistry of our bodies. So we need to understand that when we consider this issue of science and mathematics, and really what is going on when we write down, as I go to it a little bit, don't be afraid of the mathematics that I will be referring to. You cannot just simply say, particularly when it comes down to mathematics, which I'm just about to address, I'm not just simply dancing to my DNA, as Dawkins would claim. That would mean that I'm just a robot, a very complicated robot, which is putting all sorts of ideas together. No. We are far more than that. And mathematics exists without that walking robot, which happens to be talking, which is me. In other words, we're not that. There is something peculiarly, it exists. There is something very pure, period, about mathematics, but there is something which is an entity. Even those who are not Christians realize this, that mathematics is not just a language. Mathematics is representing something hugely important, which is talking about the very principles which really govern our whole universe. So now I'm coming on to this question. Well, really, what is it then? What is mathematics? You see, that number system, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, that we happen to use, it came from the Arabs who were using it many centuries ago. And it's come from systems of writing which go all the way back to the Greek times and possibly even before that. But this concept of number is something very, very important and very real. But it's not something that I can actually grab and say, oh, I've got a 1 here, or I've got a 2 here. So what then is mathematics? Well, it's connected, as we've already seen, with abstract codes and information. And it's connected with it being a language, but the language is not the same as the material. But I then made the point, and I'm making it again now, that the message is not the same as the code and the language. So although mathematics can be likened to a code and a language, it's actually carrying a message. It's carrying a principle of understanding, which is why there is something here which is rather profound, which I want you to understand. Even if you're an artist here today, I've got something for you, because there is a connection with beauty, as we shall see a bit later. So please don't think that seriously now. I'm not trying to drum all the equations and all that sort of thing, which I will come to. I want you to see that it's representing something beyond just the scribbles that will be written down. For instance, the Morse code here, which you've got here, dashes and dots. Well, that clearly is not important of itself. It's a coding system. And it's actually carrying the message, John loves Mary. John could have written it in the sand and told everybody on the seashore that he loved Mary. And it's expressing a deep and important thought. So communication can be with words, and those words carry a huge meaning. And it's the same with mathematics. It codes for a very precise carrying of meaning. And that's really what I'm getting at here. It's really carrying the concept of ultimate truth, at least in the science. So it uses logic and symbols, yet the message can be much more powerful than words can explain, which is why there is something rather profound, particularly in the language of mathematics. Those of you who've done maths, and that won't be everybody here that's listening to me and watching this video, it won't be all of you, but some of you will have done particularly applied mathematics, and even in the pure mathematics this applies, where when you actually get everything working in your mathematics, you have this sense of it clicking together, that it really is working, particularly in the applied maths, which I've done. And these are not Christian concepts. The Platonic idea of the Greeks, Plato, of course, I'm thinking of here, that there is something abstract and there is something material. Actually, there is some truth in that. It's not that this is entirely non-Christian in its origins, but of course, the Greeks took it to the extent that they were trying to bring down everything to a god of their own making, and that's where it goes wrong. But nevertheless, just on this point, they're right, that there is a sense that everything works, and there is something rather profound about the mathematics. Roger Penrose has written this book. He's written a number of books from Oxford. He's written the book, The Emperor's New Mind, and I would recommend you reading this, because a lot of it is true. There is a sense of an understanding in mathematics. If I've concentrated hard, he says, for someone on a mathematical problem and someone engages me suddenly in conversation, so he's really immersed in the maths, then I would find myself almost unable to speak for several seconds. This is not to say that I do not sometimes think in words. It's just that I find words almost useless for mathematical thinking. So if you're immersed in a mathematical problem and you're trying to make the X's and the Y's and the A, B, C's, which all represent something in the physics, all combined together, then if you really get immersed in it, you live and sleep that problem, and then you crack it. And that's what Roger Penrose is referring to. So how is it real? Well, it is real, and yet it is not defined by matter and energy. The universe has a third fundamental quantity, and that is information. Now, in order just to bring this point home, let me quote to you Thomas Nagel. We just thought about Roger Penrose, but Thomas Nagel is probably the most, in my view, he's the most honest atheist. So even though I don't agree with what Nagel believes, which is in atheism, he knows the limits of his atheism. That's why I think he's being honest. And he talks in materialist terms generally, and we would say, like all humanists and atheists, that he's a materialist, and he is normally, you would say, these people are reducing everything to molecules. And he says here, materialist naturalism leads to reductionist ambitions because it seems unacceptable to deny the reality of all those familiar things that are not at first glance physical. So he's saying that people really cannot deny that there are some things which you cannot define by some formula or something which is to do with physics and to do with experiments. But if no plausible reduction is available, and if denying reality to the mental continues to be acceptable, that suggests that the original premise, materialist naturalism, that everything just boils down to atoms in knocking around in space for millions of years, that is false, and not just around the edges. Perhaps the natural order is not exclusively physical. Now, this does not prove God. Let me be at pains to say this, but it does prove that there is something non-material going on in the universe, which is a signpost to something more, as we shall see. Now, let me tell you something else about the mathematics. You find that the same maths actually works in many disciplines. Now, this is extraordinary. And not at all is it just Christians who've seen this. Eugene Wigner, who was the Nobel Prize winner in his day for mathematics and the brother-in-law to another famous physicist called Paul Dirac, said that the miracle of the appropriateness of the language of mathematics for the formulation of the laws of physics is a wonderful gift. Well, if there's a wonderful gift, there must be a giver. So Wigner is implying that there is something more in the universe here. A wonderful gift which we neither understand nor deserve. We should be grateful for it and hope that it will remain valid in future research, and that it will extend for better or for worse to our pleasure, even though perhaps also to our bafflement, to wide branches of learning. He was an expert in quantum physics and worked in a similar area to his brother-in-law, Paul Dirac. Now, this amazing consistency of mathematics cropping up, the same maths representing different physics in different disciplines, is really quite extraordinary. Let me illustrate a few examples. I'm going to put all this up here because otherwise it's going to be something you won't understand in just a few seconds if I just put it up briefly. So I'm going to put the whole slide up here. I know it's a bit frightening, but let me just illustrate the point I've just made about the same maths appearing in different disciplines by representing three constants, which anybody who's done a bit of engineering will have come across. You'll have come across the natural base for logarithms, which is a number called or labeled E, 2.71828, and it goes on, right? Now, most of you probably haven't heard of that, but most of you will have heard of pi. Pi is, of course, the ratio of the circumference of a circle to its diameter, and it's always the same. It's just over the number 3, and it's actually 3.141592653, and so on and so forth, and it never ends. Now, there's another little thing here which you probably never come across, most of you, and that is something we represent as I. And it represents the square root of a -1. And if you like, it becomes the basis for a whole branch of mathematics, which we call the mathematics of imaginary numbers. Now, when people first started looking at the numbers sequence 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and all going all the way up to infinity, they said, well, why can't we go the other way? So they started thinking, let's go from -1, -2, -3, -4. And that means that we owe something. If we're dealing with money in the shop, then the minus means that we owe something. You know, -3, we owe £3, and so on and so forth. And the banks, of course, get very interested in that because they then might do some interesting loans where you have to pay back not only the £3, but something more. And so many financial institutions understand negative numbers and positive numbers, constantly using them. But then somebody came along and said, well, why don't I just mess about and play with the idea that there could be, even though I can't write it down, a square root of a negative number. As you probably know, if you multiply any two numbers together, even if they're negative, you always actually get another number. And if you multiply two negative numbers together by themselves, if you multiply a -2 by a -2, you get +4. If you multiply -1 by -1, you get +1. If you multiply any negative number by itself, you always get a positive number. So that means that you can never work out in reverse the square root of -4, because it's certainly not, it's not -2, because if you multiply -2 by itself, you get +4, you don't get -4. So somebody said, who was sort of just in a ivory tower of mathematics, just playing around with numbers one day, he said, well, why don't I just represent that as something which, I don't know what it is, but I'll just call the basic square root of -1, we'll call that I. And then he started building up a whole mathematics based on that symbolism. Because to be frank, 1, you might be so familiar with it, you say, well, 1 immediately means that I got just a single apple or a single pen or a single this, that, or the other. But you have to admit that the 1 that you write down is simply a symbol. Well, why can't we have a symbol to represent square root of -1? Well, nobody thought this was any use until some people started realizing that this mathematics was actually connected with something which is to do with cyclic behavior. What do I mean by that? Well, if you've got a Rolls-Royce RB 211 or whatever engine you're looking at, Rolls-Royce Trent engine, and you see it going round and round, okay, then you've got something which is cyclic. And people began to realize that this purely imaginary number, the I part of a number, the imaginary part, can be used to represent things which are cyclic and repetitive. And then you've got another part, which we call the real part to this number. So it's really an extension of the real numbers into an imaginary part as well. And then Euler came along and he said, actually, e to the I pi plus 1 is 0. In other words, he connected amazingly I pi e, which is the natural base for logarithms, and 1. Now that's extraordinary. And then you've got Euler's formula there, which if you're doing big time engineering, you'll have come across that. So now cyclic behavior occurs in all sorts of disciplines. But before I come to that, let me just mention this, that there are some things in mathematics which people only discovered really in the last 100, 150 years, 200 years or so. This is not that old, this part of the mathematics. Just doing a simple square root where it's no longer a whole number. We call those surds. The square root of 2 is not a whole number. The square root of 4 is a whole number. Pi itself is not an easy number to deal with because it just goes on and on and on. And some people spend their whole lives memorizing pi. Can't think of something more ridiculous to do, but that's what some people do. And there are fundamental algebraic relationships. Some of you will have done this at school, that you'll have had to work out a quadratic equation and the solution to it. Now, you probably know that if you've got ax squared bx plus c, then the solution is x equals minus b plus or minus the square root of b squared minus 4ac all over 2a. You might have said, what and why is that important? Well, it actually occurs, and this is now the nub of what I've really been trying to say. There is a connection with this rather interesting mathematics where sometimes you could get a square root where the b squared minus 4ac is negative, and you're dealing with a square root of a negative number, like I was saying earlier. And this occurs across all the disciplines, physics and chemistry. And you get complex solutions, and that's what I was aiming at here. Now, let me give you some sort of illustration of this where, no, the illustration will come a little bit later on some of these matters, but I will come back to that. I haven't got that slide just at this point, but I will give you an illustration where this occurs across all disciplines. We'll come to that. Just take it that that is the case, that this, we call it stability theory, actually occurs across many disciplines. Now I need to build in something else here. Did you know that there are some things, some constants, which link with beauty and the art world? I know I've got some artists listening to me, and let me connect the maths with art. Some people get afraid about the golden ratio. They think, oh dear, this is mysterious. You're going into sort of sub-magic ideas. No, no. It's just simply that there is some very interesting concepts which are out there, and people only realize this in the last 100 years or so. A chap called Fibonacci was messing about with numbers, and he started writing down 0 and 1, added them together, got 1. Then he added 1 and 1, he got 2. Then he added 1 and 2, he got 3. 2 and 3, he got 5. And he noticed that he was forming a series. And we call this the Fibonacci series. And if you take one number and divide it by the number before, it gets close to, even when it's 8 over 5, 13 over 8, it's a bit better still. 21 over 13, it gets even better. It starts converging to this number, 1.618. And the ratio of the numbers tends to this golden ratio as the numbers get larger. Interestingly, the inverse, which we call 1 over capital phi is just a label, is 0.618. So this number has a special property that 1 over that number is 1, or in this case, it's 1 1.618, the number we had, minus 1. So it's a bit of an odd property. Now, let me explain this in picture form. Suppose we have a line and we bisect it such that the ratio of the smaller part to the larger part is the same as the ratio of the larger part to the whole. So we're going to say that the ratio of B, which is the bigger part of where you bisected the line, to the whole line length, which is A, we're going to say that is phi. So that's obviously going to be less than 1. And we're going to say that we're going to say that's the ratio of the larger part to the whole, right? Is going to be the same as the ratio of the smaller part. So you've got to bear with me here, which is the A minus B to B is then going to be the same as B over A. So let's put that in. But instead of just putting it in, let me just go back there. Instead of putting it in as B over A is equal to A minus B over B, we're actually going to substitute for B is equal to A phi in that. So we're going to write that as 1 minus phi, or A minus phi A over B, which is then means that you've got B over A is equal to 1 minus phi times A over B. But B over A is phi. So actually we've got a formula here, which is that phi squared, because we can put the B over A on the right-hand side, multiply it, cross-multiply it on the other side, and you end up with you've got a formula for phi, which is that phi is equal to root 5 minus 1. This is the golden ratio. And 1 over phi happens to be 1 plus that, and it's labeled capital phi. It's a property of this particular ratio. We call it the golden ratio. Now, if we extend sideways by B, so you've now formed a square length B, okay? Then if you keep on doing that, and so that you slice across where the square is, that then gives you a rectangle, which itself can be split into a golden ratio. You keep on doing this, slice off the square, and you get left with a little rectangle, which you then do the same, and you bisect it at the golden ratio. That means you're going to get a golden spiral. And you actually find that the angle that you sweep through is what's called the golden angle. This golden angle is the angle where B over A is equal to phi. It's 0.618. And that means that the angle is approximately 137.5. A, so what you sweep through, and B are in the ratio such that B over A is 0.618. The angle then that you get at the middle is 137.5. The outer angle is 222.5, 360 minus 137.5. Now, this is where it gets amazing. The angle between successive florets in some flowers is the golden angle. 1, if you look at the picture there, 1, 2, right? Then 3, you're approximately going through the golden angle. Then you go from 3 to 4, it's another golden angle. 4 to 5, another golden angle, and so on. Now, that is quite amazing because it really does work in nature. Not only that, you'll find that the number of spirals invariably is a pair or triplet of Fibonacci numbers where you've got seed pods. A pineapple is a clever one. I often joke to my wife, have you got a Fibonacci pineapple there? And I often check it, and it's usually 5, 8, and 13. If it's quite a big one, then it'll be 8, 13, and 21. And you can see on that picture that you've got spirals going from left to right, from the bottom, left to top right. And then you've also got a spiral which is a bit more at a steep angle going from the bottom right to the top left. Actually, if you look carefully, there's yet another one which is to do with this time. It's yet another one which is actually slightly at an angle again, which is to do with a third set of spirals, which is difficult for me to show you unless I was actually doing the lecture personally. But you can actually see 3 sets of spirals on any pineapple. The sunflower, I've actually marked them for you, the blue, red, and yellow, and those numbers are invariably Fibonacci series numbers. So it occurs through the natural world, but it also occurs in art. People do this without realizing it. They will actually use the Fibonacci series and the golden ratio. Amazingly, the Areopagus in Athens and other well-known Greek masterpieces in architecture actually used the golden ratio. Leonardo da Vinci, with his Mona Lisa picture, also used the Fibonacci series. And many of the works of art, like Notre Dame Cathedral, as you can see there, also used the golden ratio. It is found in many shells. It is found in sunflower seeds, pineapple seeds, found in cones. And you'll find that so many buildings have this. The pyramids also use the golden ratio. The phi in this picture is actually 1.618 in this particular picture. And if you actually apply Pythagoras to that, you'll find that the phi squared is equal to 1 plus phi squared. And that number, of course, is 1.618 to satisfy that formula that I had earlier. So the pyramids, the Egyptians, therefore, knew about the golden ratio. You've heard of Darwin saying this about a peacock feather. Oh, it's a small, trifling particulars of structure. Surely from a Darwinian perspective, that's what he's saying, as Charles Darwin is actually writing. He says, the small, trifling particulars of structure often make me feel uncomfortable because they're not small and trifling. The sight of a feather in a peacock's tail, whenever I gaze at it, makes me sick. Why? Because that beauty that we see in the peacock feather, and by the way, the peahen, probably couldn't be bothered at all by the eyes that it sees in the feathers of the peacock strutting around, showing its tail. But they're very beautiful to us. Shall I tell you what the beauty is connected with? It's connected with a number of things. The blue and the green is an iridescent blue and iridescent green. Stuart Burgess, my colleague who put the book together, Wonders of Creation, he and I actually comment on the peacock feather, and particularly Stuart comments on the fact that the light as it comes down onto the barb at the blue section, that light causes a color which is entirely by reflection. And it's due to the bending of the light as the light goes through that tiny little layer and then is reflected, splitting the white light into a component which is predominantly what escapes from that surface finally is predominantly blue. The red, it doesn't escape. So that's why we get the blue iridescence. And the green is a slightly different layering. whereas the pigments in the rest of the feather are what give you the brown and the purple. Well, this raises a lot of issues. It's not my main point tonight, but it does mean that the barb is actually changing its structure as it goes through this mathematical cardioid formed by the iridescent blue. That's what that deep blue is. It's called a cardioid, where it's not a circle. It looks a bit like a circle, and then it comes in a V-shaped form. Now, that mathematical cardioid shape, would you believe it, has a golden ratio in it? Because if you measure these two lines, and it's in the book, Wonders of Creation, this point, they are roughly, it's not exact, but it's very close to the ratio 1.618. So that's an amazing point, that the ratio of those two lengths is either the shorter to the longer 0.618, longer to shorter 1.618. Now, this carries on. Fibonacci numbers are involved in art and musical composition. So an artist will naturally not put, for the lighthouse picture there on the left, he won't be putting the lighthouse in the middle of the picture. He'll be putting the lighthouse slightly to one side because it looks better. Sometimes they do it without realizing. Sometimes musicians and musical composers are doing it deliberately. It is believed that Bach discovered the Fibonacci ratio, and many of his pieces used the Fibonacci and the golden ratio in their compositions. So that is happening a lot in some of the later composers. But it amazingly crops up even in the musical ratios which are used for the piano. The original piano was something like a harpsichord, and the original frequency for A, which all the orchestra tunes up to, is 440. Now, if you look at C, which is in the fifth octave, A is the A4 means that it's in the top of the fourth octave, but now we're moving into the fifth octave, imagine on the piano. Now, C above the 440, which would be the top C, it's not the middle C, is actually C4, but this is the C above middle C. It's actually 528 cycles per second. Well, that compared with the root octave, which is the red one there, is actually 6/5, which is 3/5 times 2. These are all Fibonacci numbers. And if you look at C sharp, right? So imagine you're doing A to C, that's a minor third, but now you're doing A to C sharp, that is a third, it's a major third. That's 5/4, it's 550 over the 440, which is 5/8 times 2. So that actually gives you a third. So a third involves not 3/5 times 2, but 5/8 times 2. And when you go to a fourth, it's 4/3, which is 2/3 times 2. And when you go to a fifth, which is, imagine you're playing now A, C sharp, and E, right, which would be your nice sounding major chord. That top one, the E5, as it's on this chart, is 3/2, which is again all to do with Fibonacci numbers. So all the major chords are involving Fibonacci numbers. Now, if you try and do that on your piano today, you'll find that it doesn't quite work, because now on a tempered frequency, tempered tuning, which is what we use now for pianos today, we don't quite have those frequencies. That's now what I've now revealed as the equally tempered frequency. What does that mean? Well, I won't go into all the detail here, but it just means that you can transpose from a keyboard which was originally tuned for C in the old days. You couldn't transpose to E, and you couldn't transpose to A. But now with equally tempered frequencies such that the gaps are all the same for the different, well, you're getting it very close to being the same. It's not exactly the same. That now means that you can more readily transpose. This also, by the way, shows you why somebody playing in E flat, a particular piece, will sound different to somebody playing in C. Those who are actually attuned to music know that some chords sound richer in one key than they do in another. That's because we now use equally tempered frequency scales. So let me just complete this bit about music. You'll hear the beautiful music of Clair de Lune. It is well known that Debussy, but there's other composers did this, actually composed their pieces such that the amount of time on one particular theme, the amount of bars, was compared with other themes in the ratio of very close to the golden ratio. Bach is full of it, Debussy is full of it, and even Beethoven's Fifth, people have discovered golden ratios in that. It's really quite amazing that some of the most beautiful music has golden ratios in it, which is hardly surprising because Johann Kepler said geometry has two great treasures. One, the theorem of Pythagoras, the other, the division of a line into extreme and mean ratio. The first we may compare to a measure of gold, that's Pythagoras. The second we may name a precious jewel. Now Kepler actually was a person who believed in God and believed, as we understand it, in the biblical understanding as to how we look at the world. He, of course, was the person who understood the motion of the planets, but he's acknowledging here the golden ratio, which occurs naturally in nature. Just so that you get some real thirst for doing some of this yourself, have a look at this. Examples of symmetry. 1 times 8 plus 1 is 9. 12 times 8 plus 2 is 98. 1, 2, 3 times 8 plus 3 is 987. And look how amazing patterns are developing. 987, 6, 5, 4, 3, and then eventually 987, 6, 5, 4, 3, 2, 1. That's quite an amazing example. Now, of course, this is because it's working in base 10. If you were working with counting in a base, different base, that means the way you start writing 10, we're writing 10 with the notion that it really means the number after 9. But of course, some people might want to use a number scheme, which is perhaps a number base, which is 16. We call that hexadecimal counting. Well, then you won't see these patterns emerging quite so easily, but you will get a number system which is based on that particular base, producing a particular pattern which is to do with that base. In this case, it's running from 1 to 9, which is just short of the base 10. Here's another one. 1 times 1 is 1, 11 times 11 is 121, 111 times 111 is 12321. 1111 times 1111 is 1234321. And then next time it becomes 123454321, and so on and so forth. It's quite amazing, isn't it? That's all to do with, of course, the base which one is using. Now, I'm going to get a little bit more complicated in this closing section. I've got 10, 15 minutes more to share with you. If you're not quite with me up to this point, go and get an ice cream out of the freezer and don't switch off, because I've got something very interesting coming. You don't need to understand these equations, but some of you might. Now, remember I said to you that when I started using that square root of -1, okay, I said to you it's all to do with cyclic phenomena. Well, I'm now going to actually illustrate that in this section, and I'm going to show you what really happens when you actually do this you actually find some very interesting connections across the disciplines. So I'm going to show you this now. I'm going to show you the disciplines which illustrate this. So just bear with me. I'm just made a mistake in my, sorry, I need my talk up. Here we go. Sorry, I need my crib sheet, which I'm using here. And just bear with me. I just did a stupid thing. I got too excited and I lost my talk, which I've also got next to me. Okay, here we go. So remember I talked about this cyclic phenomena, right? Well, it's quite amazing that this cyclic behavior, which is represented by complicated differential equations. You may have heard of the wave equation. Some of you may have heard of the first one, which is Laplace's equation, which is to do with heat diffusion. Well, that same equation occurs in low-speed fluid flow. It occurs in electromagnetism. And the wave equation, right, occurs in strings, of course, but of course it also occurs with waves, and it occurs with sound, it occurs with light, it occurs with radio waves, it occurs with electromagnetism and with water. So waves occur in all sorts of places. So that square root of -1 stuff that we did earlier, that really does occur right across the disciplines. And I find that astonishing. It may not excite you, but it certainly excites me as a mathematician. And Einstein said, how is it possible that mathematics, a product of human thought that is independent of experience, fits so excellently the objects of physical reality? Mathematics unlocks the principles of how the universe basically runs. Johann Kepler, whom I quoted earlier, who talked about the wonder of the golden ratio, he talked about it being a real pearl which had been found, or a precious jewel. He now says, I was merely thinking God's thoughts after him when he discovered his motions of the planets. So the power and coherence of mathematics now, I'm going to illustrate in two things, which is in the advanced mathematical bit. You need an ice cream for this bit, but don't worry about the detail. Just get the words that I'm speaking. Some of you have heard of quantum physics, all right? Well, quantum physics is actually governed by Schrodinger's wave equation. It's a wave equation like I was talking about earlier, but it's actually got another little term on the right. And it actually ends up with two solutions, but not just two. It ends up with 4 solutions. So when people wrote down the mathematics for the wave equation, and it's called Dirac, because Dirac did this, he was the brother-in-law to Eugene Wigner, whom I mentioned earlier. So when Dirac wrote down the mathematics for governing what was going on in quantum mechanics, the nature of matter, people already knew about the electron, right? So they weren't surprised, and Dirac wasn't surprised, that 2 solutions represented the electron. But what he wasn't realizing, until he then thought about it more carefully, is that there was 2 other solutions which represented something else, which he was not yet discovered, and it was the positron. This showed the tremendous power, predictive power of mathematics, that he would now have to tell the experimentalists, go and find the positron. And would you believe it? They found it. And Schrödinger, who was also in the same field, says, I'm very astonished that the scientific picture of the real world around me is very deficient. It gives a lot of factual information, puts all of our experience in a magnificently consistent order, but it is ghastly silent about all and sundry that is real, really near to our heart, that matters to us. It knows nothing of beautiful and ugly, good or bad, God and eternity. So although he was pleased with the way mathematics went, and he was the one who wrote down Schrodinger's wave equation, which is there, right, which we've just been talking about, Schrodinger himself realized that there was a limit to what his own great work could do, because he hadn't yet acknowledged God in his thinking. Boltzmann, you may have heard of him. He was a great person who understood my area of thermodynamics, but he actually was swung over by Darwin. In my view, all salvation for philosophy may expected to come from Darwin's theory. How sad that this person ended up committing suicide, and his grave is there with his famous important law about entropy written down. But that's all he could give us. Sadly, some mathematicians went crazy, even when they'd done some great work. Let me just tell you something else from my own work, which is in aerodynamics. Boltzmann is one person, but how about this person? This is Ludwig Prandtl. He actually did great work on understanding the airflow over wings, and it's called Prandtl's boundary layer theory. You don't need to worry about the mathematics here, but suffice to say that using carefully worked out symbols, he could say that there was a different physics close to the wing from the outer flow. And by joining the outer flow physics, the mathematics of that, to the inner flow physics, and realizing that Reynolds number, which is written there as rho v over eta, where rho is density, v is velocity, eta is the viscosity, the dynamic viscosity. And when you actually write that symbol, you get a symbol which represents the competition between these two parts of the problem. And what he found was that you could link the two together and understand the boundary layer. It's just an illustration of what I was meaning earlier when I said that when you get it right, it all fits like a jigsaw. And there is a deep sense of pattern and aesthetics. You get this sense that everything clicks together, a bit like the aesthetics that you get from music. And there is a strong connection of things being done properly with the music that a lot of mathematicians really do love. Einstein was a brilliant violinist. So when you actually do things properly in mathematics, it leads to a great understanding of the problem, but you also have a sense, a bit like music, that everything is beautiful. So when you get mathematics right, then you have great predictive power. So let me illustrate from, for instance, Newton's gravity. That's a very simple formula there for understanding how two masses, big M and little m, the sun and the planet, work and the force between them. And Kepler, using such laws, which came from Newton originally, made predictions about how long it would take for a planet to sweep through a particular arc. And he found that it was always the same time for a given planet, even if it was an elliptical orbit. This led to Kepler's laws of planetary motion, which are used even today for NASA as they send probes to Mars and other places in the universe. What I'm trying to point out, though, is the simplicity of the formulae. They're not that complicated. Usually, the simple ones are when you get it right. Einstein's famous energy equals mass times speed of light squared showed that energy and the speed of light are connected. And of course, famously, when the bomb at Hiroshima and Nagasaki, when those bombs were dropped, it demonstrated awfully that that energy is very, very real and huge. There is a connection that Einstein had predicted, and that terrible event in 1945 demonstrated it. Let me come to Maxwell, who was a brilliant scientist, Christian, who loved the Lord. He wrote on the Cavendish laboratory door, there at Cambridge, he wrote the words, "The works of the Lord are great, sought out of them that have pleasure therein." Psalm 111, verse 2. It was written in Latin, and it's there today on the Cavendish laboratory door. Maxwell's equations are actually 4 equations which people had discovered before. Gauss had discovered the first one. You don't need to worry about all the detail of these. But Gauss had discovered the law of electricity, which is to do with the diffusion of the field, the electric field E. Faraday, who was a very great scientist in his day, not a mathematician, but he had written another law about the connection of electricity with magnetism, represented by H, the magnetic field. Then there is Gauss's law for magnetism, which is a different law, got a similar look, but it's not exactly the same. This is a Gauss's law for magnetic field. Then there's Ampere's law, which connects the magnetic field with the the rate of change of the electrical field. We call that Ampere's law. Now, brilliantly, Maxwell took all 4 laws together and said, here, guys, there is a wave equation. Remember I talked about waves before? And the I that you get in the maths, okay, represented circular behavior. Well, he showed that light is an electromagnetic wave. And by showing that there was 2 parts to that wave, an electric field and a magnetic field at right angles, he was able to say that that electromagnetic field would go at a particular speed. Now remember what he said on the Cavendish laboratory door? The works of the Lord are great, sought out of all them that have pleasure therein. He gave glory to God for what he was doing. And his brilliance predicted that there would be a wave and that it would travel at a particular speed called c. That speed he predicted would be roughly, well, it's not exactly this, but it's roughly 300,000 meters per second. That's a lot of meters per second. Well, eventually Millikan and other people got together a mechanism, an experiment for measuring the speed of light. And guess what it was? Almost exactly what Maxwell had predicted. And it's based on 2 numbers which are to do with the electrical field and the magnetic field. This is one of the most greatest discoveries ever made. And it shows the power of getting the maths right. It means that you can predict things. So mathematics not only has predictive power, but when it's done correctly, it has elegance and beauty. Back to Roger Penrose again. He said a beautiful idea has a much greater chance of being a correct one than an ugly one. Compare that with Dawkins, who said, the universe we observe has precisely the properties we should expect if there is at bottom no design, no purpose, no evil, no good, nothing but blind, pitiless indifference. And he said on another occasion, my brain is just a lump of meat. I have the music of Schindler's List going on, because from this way of thinking, it led to the disaster of atheism applied literally to the social structure of Germany. And Hitler based much of his thinking on Darwinism. My dear friends, when Dawkins said my brain is just a lump of meat, he was making a crucial mistake. He said this to a friend of mine, actually, who was speaking to him in Oxford. And that's where this has come from. He said it in frustration, but he was not realizing that rationality transcends the very instrument that he's using so cleverly, which is his brain. And even Thomas Nagel said in the book Mind and Cosmos, evolutionary naturalism provides an account of our capacities that undermines their capacities, their reliability, and in so doing undermines itself. You see, an atheist really has no basis for even why he can think at all. Remember Haldane's quote that I had earlier? And Nietzsche said this: God is dead, God remains dead. We have killed him, yet his shadow still looms. How shall we comfort ourselves, the murderers of all murderers? Eventually, Nietzsche died. And somebody wrote on the wall, Nietzsche is dead, God. Friends, when you push God out of your thinking, you've lost the basis entirely of reason. We need to realize that mud to mathematics by mindless evolution does not work. And beauty has no understanding if in fact we say all this wonderful mathematics has come about without a mind behind it. If we were to play Chopin's Nocturne, you know, this beautiful music obviously has an author. And of course, that author is Chopin himself. Music is really like mathematics, pointing to God. And God has supremely demonstrated himself in the Lord Jesus Christ. Psalm 103 says, know you that the Lord, he is God. It is he that has made us and not we ourselves. I missed that slide and I missed that one. But let me come to my conclusion. The nature of mathematical ability implies strongly a transcendent God. We are made in his image. We reflect his own transcendence. That means he's not defined by what he's made. Beauty is an expression of our being made in his image. Mud cannot produce logic, mathematics, and beauty. So in conclusion, man is made in the image of a transcendent God, not defined by what he is made. This gives the basis of rationality, gives the basis of beauty, and it also means that we are responsible before a holy God. My dear friends, this means that God has revealed himself, and he's revealed himself supremely in the person of the Lord Jesus Christ. In John 1 verse 3, it says, in the beginning was the Word, and the Word was with God, and the Word was God. The same was in the beginning with God. All things were made by him, and without him was not anything made that was made. Thank you for listening to this. I'll stop there and I'll hand back over to Simon. Thank you, Simon.
Thanks, Andy. It was a great presentation and really fascinating to see the design and intricacy behind God's design and creation. And I did take your advice, by the way, Andy. I did take your advice. I did go and get my ice cream. So,
oh, excellent. Good. And can you show it to the audience? Because I can't see it, just to prove that you got one. He has as well. Well done.
There you go. There you go. I finished it.
He got his ice cream and he's finished it.
I finished it.
So,
well, thanks.
Are there any questions that people might have?
There haven't been any questions come through. Some of them might be still stuck on that maths equation you gave them.
Yeah, I'm still trying to find the solution to it. But
when you were talking, I did think about something I heard last week from the States, from the Black Lives Matter movement. There was a lady on the news, and she was basically saying we should reject 2 + 2 = 4 because it's a Western construct. It's something that we should get rid of. It's a sort of imperialistic Western concept. But obviously that's not true, because maths doesn't have its foundation in the West. It has its foundation, obviously, through God. Yeah.
But actually, may I just say, she's got a little point in one area, and that is that you don't need the actual symbol 2 and 2 and the symbol 4 in order to have in your mind the idea that 2 things and 2 things makes 4. You could express it in another, I'll use a mathematical term here. You can use a different, what we call base. As you know, on the computers, you've got a base 2. So you've just got 1s and 0s, right? And when you write 1, 0, it doesn't mean 10 in the usual sense of the word. It means that you've now got 1 times 2 to the 1 and 0 times 2 to the 0. So it actually becomes 3 and 4 and stuff like that in our terms. So when you change the base, then you can change the symbols. So if she doesn't like the symbols, well, you just make your own, but you still can't get rid of the concept. As you said, that comes from God.
Yeah. Well, she probably wants those symbols to be logical when a paycheck comes in at the end of the month.
Exactly. I'm sure she does. Yeah.
But I thought it was amazing the lengths people will go to get rid of things when they want to get rid of God, and when they want to get rid of the structure that's held up Western civilization.
Very true. Very true. Thank you anyway, Simon, for that point. And there may be other questions come up later. And if people want to ask me a question, seriously, you could send it to Simon, and because it's on the maths, you might say, well, I'll send it on to Andy, and I don't mind trying to answer that. But there are some interesting issues here. That's all I'm trying to get over, is that maths has, it's like a massive signpost pointing us to God, pointing us to the truth. And of course, the Bible goes further and says that truth has become a person, the Lord Jesus Christ.